Hi, I'm Dr. Tom Calabrese, and welcome to this edition of Insights into Computer Science. In this week's edition, we'll be looking at programming languages and the things that they have in common. Many students want to know how many programming languages I know, or which one is the best, or which is the easiest or the hardest to learn. It seems to me that one of the misconceptions about computer science is connected to the plethora of languages that are out there for us to choose from. These questions, quite frankly, are irrelevant to a large extent because trained computer scientists will tell you that the language is a tool, and whichever tool makes solving a problem easier is the best language to use in that situation. Personally, I worked in consulting for many years, and when the boss said, we'll do the project in this language or that language, I knew that either I would learn the language or give up the assignment and, well, ultimately the money. I learned quickly to learn how to learn new languages, which is really not all that difficult, especially if you have a strong background in computer science. Turns out that languages actually have a lot of things in common, and if you know what to look for, you can come up to speed pretty quickly in any given language. Now, in a previous episode, we took a look at learning Python. We accomplished this through a learning by exploration process that I helped guide the viewer through. For most people that I've worked with, this is a nice and comfortable way to get going with your first language. Then if you have an interest and the itch, well, then the rest starts to fall into place as you continue to explore, experiment, and enhance your way to competency and fluidity in a given language. There are so many programming languages out there right now, it's hard to count them all. To start with, there are different types of languages. There are procedural languages, object-oriented languages, parallel, concurrent, special purpose, scripting, server-side, and functional languages. Examples of these are C, Fortran, BASIC, Pascal, PL1, COBOL, and ALGOL, all of which are procedural languages created in the 60s and 70s. By the late 70s and early 80s, we saw an emergence of things like Ada and C++. This kicked off an object-oriented era. Specialty languages like Lisp and Scheme for AI followed separate growth paths, as did Prolog for logic-based decision-making programming. Scripting languages like Perl, JavaScript, PHP, VBScript, and ASP grew in popularity. SQL for databases and HTML for hypertext authoring have become commonplace. Most recently, Java, C#, and Python have all become enormously popular object-oriented programming languages. Python is now the most widely used general-purpose language. But to the novice, this may seem overwhelming. Now, instead of asking questions like how many languages you know, think about the questions like which one is best for this type of problem, or what do they have in common, or what does the programming environment look like for a particular language, or even how quickly can I master the basics of a particular language. Okay, so let's take a look at some of the basics and go from there. In general, languages fall into one of three categories: compiled, interpreted, or hybrid. Compiled languages are things like C or Fortran or C++. Interpreted are languages like Python, R, HTML, SQL, and BASIC. Hybrid languages would include Java because, yes, you do compile it, but you also need the bytecode interpreter resident on the system that you're using or running the program on. C# has the JIT or just-in-time compiler that goes along with it. Interpreted languages use a read, evaluate, and print loop to process programs and instruction at a time. They are typically easier to start working with, but they're often slower and less efficient than compiled languages. A main advantage of the interpreted language, like, say, Python, would be that inside the shell, you can use a command, observe changes, then proceed one step at a time to get to your required answer. It is designed for exploration. Of course, the idle IDE provides the programmer with the same look and feel as the compiler type programming languages, but even there, the programs are executed in the one loop at a time manner. By contrast, compiled programs are created first, and then they need to go through the build process before they can be tested. This is better aligned with our previously discussed design methodology. Compiled programs are much more difficult to construct, debug, and work with in general, but they are typically faster, they're optimized, and more durable than the interpreted counterparts that we would create with languages like Python. As you can see, the build process in the C programming language requires that the programmer first code their design in a file with a .c extension. This file is known as the source code. That code is then sent to the compiler, where it is made into machine code and then optimized. That .obj file is then linked to other files that are required by the program. These files are also .obj files that are found in libraries. These files might include something like printf in the C programming language as part of the stdio.h library. When the linker finishes its job, the .exe file is created and can be run on the system. To do that, the loader is invoked to find space in memory to run the program and create the process or the running instance of that .exe. You can have as many instances as memory will support for a particular .exe file. You probably do this all the time when working, say, with Word on several documents at a time. If you just go to the task manager and look at the processes, you'll see Word 1, Word 2, etc. for each open instance of Word. These are all instances of a running process. The compile process itself is also complicated. When the source code enters the compiler, it first goes through a section known as the scanner. The scanner is the section of the compiler responsible for syntax examination. This looks for grammar errors or unrecognized symbols. From there, the code enters the parser. The parser is basically a rule checker to be sure that the rules of use are in scope in your program. Once these two sets of tests are passed, the code enters the code generation phase. At this point, the compiler takes the C instructions and recasts them as machine-readable code, compatible with your device's machine instruction set. You'll get a better appreciation of this phase when we get to our discussions about assembler language. After this is done, the code in most compilers goes to the optimizer. This is a section of the compiler that adjusts the machine code to increase the efficiency of that code. Finally, at the conclusion of this phase, a new file, the .obj file or object file, is created and the build process continues. So, you might be wondering why, after all these years, we still have not created a super programming language, one that does everything, instead of maintaining all these programs in such a wide variety of levels. I suppose that the truth is that various people have tried, but it is just that there is such a wide array of requirements that the task appears to be unattainable, practically speaking. Let's look at this from the point of view of a spectrum of programming languages. If we look at it this way, by a way of comparison, we would find that assembly language would represent one extreme of the spectrum, and non-procedural specialty languages like SQL, Alice, or HTML would be 180 degrees out of phase, representing the other extreme. Assembly language is as close to machine code as you can get. Each instruction parallels a corresponding machine code. The coding is tedious and very difficult to do for most experienced programmers. But assembler offers the engineer the most control and most efficiency in terms of access to memory and reduced instruction load. But it comes at a cost. Besides being difficult to do, it's bound to a particular hardware platform. Thus, there are many portability issues. In other words, my x86 program will work on those machines, but are not compatible with, say, a Motorola-based system. C is also far to the left in our chart, just a tad less complicated than assembler, but it's still difficult to work in. C is a procedural language. It was developed to create an abstraction over assembler code, and as such, the developer is able to port the code from one platform to the next. To see just how closely related they are, if you run C program in the command prompt under the GCC compiler with the -S switch or GCC-02-S and then a file foo.c, will leave the generated code on the file foo.s where you can see the assembler code. If, however, you'd like to see the comparison side by side, assembly versus the C code, try this. As you can see, the machine code is on the left, the C code is in the middle, and the assembler is to the right. By way of comparison, you can see just how closely these three things are related. The languages on the far right are less structured and very easy to use. Languages like SQL and HTML lack control structures and the formality of C or Fortran. SQL is a database query language and is used to reference information stored in database tables. The basic query form is select some item from a table where a condition is met. Newer languages like Python or R are also very easy to learn and are interpreted and sit toward the left of our spectrum. Java and Ada, both object-oriented languages, really represent the middle ground in programming languages. Ada was the language proposed by the military in an attempt to create this one super language for all military or government projects. Although Ada is a very robust language with many Java-like features, it was determined not to meet all of the requirements and was canceled and deemed a bust. However, the language is still around and can be found on some niche products that you might find as you look through the literature. Java was the most popular language for most of the last 15 years, but recently was surpassed by Python. C++ was an early attempt at making a procedural and object-oriented combination language. It was initially quite successful, but tended to be more difficult to use than Java and not nearly as flexible. C++ is still popular with some engineering and more technical projects like robotics-based code, but never gained the notoriety and popularity of Java. Older languages like Fortran for mathematics or COBOL for business or PL1 for IBM mainframe programming are all procedural languages and fit very nicely into their respective niches. Now, if you look at the spectrum, you will see that the languages to the left are most useful for engineering applications like robotics or networks or data communications, real-time systems, operating system development, device drivers, and things like that. Languages in the middle are more general purpose, but professional software engineers might use these languages for large-scale multi-purpose application program development. Languages toward the right are more appropriate for specialty programming, data science, and user-developed apps that are more focused in a particular business need or area that need to be done quickly and in response to an emerging business need by experts in their related field rather than by professional software designers. One of the aspects of my career in computer science that I really loved was the opportunity to work side by side with subject matter experts in various fields. We would design industry customized solutions based on their particular requirements and their knowledge and expertise. You'd be amazed at what you can learn and how much fun it can be. So now you might ask, we've covered so many differences, where are the similarities? Well, I summarize it this way. Most languages have four basic things in common. Some sort of a system interface so that they can interact with the user, the network, other programs, control structures so that they can work in an orderly way, with the exception of the specialty languages like SQL. Language elements that can be used to provide instructions to the compiler or the interpreter, and data handling capabilities. Now, we could take this a step further to show that in most of the languages on the spectrum, we can see that the system interface, for example, includes the IDE, some form of hardware access to control devices, I/O, a debugger, the user interface, which is sys-in, sys-out, or sys-error, libraries for advanced features, and possible objects. There are four basic control structures that we see in many languages. Sequencing is the first. These are functions that divert the flow of code to reusable sequences defined outside the main body of the code. We did this in Python with the def or def command. Selection, this would be the if, then, else sequences that we've discussed previously. Iteration are the repeatable sequences normally starting with the keyword for. And conditional, those are the blocks of code that keep executing as long as some condition remains true. Typically, this would be found in the while command. Languages have elements that include things like variables, keywords, built-in functions, commands to load libraries and objects, comment delimiters, operators that fall into categories of bitwise, logical, mathematical, comparison, and string operators. Finally, the data handling area includes memory management commands, network communications, formatting commands and switches, input-output commands for accessing the memory or the screen, the network, or the files, or the keyboard, mouse, or other peripherals. Data handling also includes how data typing is approached. This might be the strongly typed languages like you would find in C, or loosely typed languages as we would find or you've seen in Python. Finally, all languages require that you understand the syntax and the semantics of the language. That is, the form and meaning of the commands. With this set of things, you can investigate and start to learn any new language. Hopefully, you can see from today's episode that learning a new programming language is not really all that difficult, as you may previously have imagined. The method I recommend can be thought of as, first, understand the purpose of the language and make sure you know the types of problems it was designed to work on. Second, go through the four quadrants of the learning circle that I just defined: system interface, control structures, language elements, and data handling, and see if you can find the similarities to things you already know. Third, explore, experiment, and enhance. Find a tutorial on a language to get started. Then look at the documentation for that language and test run some already working programs to get started. Next, try making enhancements to those programs and modifications in order to test your new understanding of brand new things that you may have read about. Experiment doesn't mean watch others. It means you do it. Make sure that if you want to do something or use something in your program, you try it out in the small first. And finally, never stop exploring and creating. The more programs you write, the better you'll be able to do it. I know that learning your first programming language was really painful, and it's that way for everyone in the field. My suggestion would be to learn Python first. The reason for this is that Python was designed to be programmer friendly, and it's a very robust language that will expose you to many of the language concepts that we've discussed in this video. Then I would suggest learning C. This is conceptually different in that it is the language of memory and allows you to take advantage of many things that Python just simply cannot do, such as pointers into memory, dynamic memory allocation, and the like. This also lets you look at both ends of the spectrum and gives you skills in two really useful languages. After that, it's really up to you. Think of it as the wild, wild west and have at it. Remember that languages are just tools and they will continue to evolve and new languages will continue to be introduced. You need to be able to adapt and update your skills in various languages every now and then. Remember, in technology, every 5 years brings a whole suite of new things and technology changes. And as you go through a 40-year career or so, you'll need to be able to learn new languages quickly just to be able to keep up. Have faith and it'll happen. Until next week.